In this class, we will discuss how to test hypotheses and interpret the results when using bivariate regression. As indicated earlier, we use bivariate regression when we hypothesize that a predictor will predict variance in the criterion. The null hypothesis is that the predictor does not predict the criterion in the population. In bivariate regression, the null hypothesis is that b equals 0, or that the predictor fails to predict variance in the criterion in the population. For the example cited earlier in the class, the null hypothesis would be that BDI scores do not predict variance in suicidal intensity ratings in the population. We will test this null hypothesis with a t-test in which b is divided by the standard error of b. The degrees of freedom for this test is degrees of freedom equal to n minus p. Thus, if we have 30 participants in our study, df equals 30 minus 1 for one predictor is equal to 29. Before going on to the next slide, if b equals 0.30 and the standard error for b equals 0.06, would we accept or reject the null hypothesis? The test statistic is computed by dividing 0.30 by 0.06, resulting in t equal to 5.00. Since the critical value equals plus or minus 2.045 at 29 degrees of freedom, we would reject the null hypothesis. We would conclude that BDI scores at intake are significant predictors of suicidal intensity ratings in the first 6 months of treatment. Based on the original finding that R equals 0.43 and R squared equals 0.1849, we would say that BDI scores can help to predict 18.5% of the variance in the criterion. Also, because B and R are both positive, we would say that increases in depression scores predict increases in suicidal intensity ratings. As noted earlier, when correlation between x and y equals 0, b will also equal 0. Thus, in bivariate regression, if the correlation coefficient is significant, b will also be significant. This is why many researchers will discuss the finding of a significant correlation between x and y by saying that x significantly predicts y.